Perfect. So yes, I'm going to be talking to you about my first postdoc last year, which was on using plasmonic multipod clusters as bright and efficient emitters of magnetic light. And I've been a postdoc with Alex, and this was a collaboration with Mona Traeger Delapure at ICMCB, and along with Sebastien Badeau and Mathieu Mivel in Paris. I'll start by talking through some of the motivation, specifically around the fabrication and tailoring the interaction Hamiltonian. A little bit of theory along the solution of what's called the Thomson problem, and a little bit about quasi-normal modes. Then the results, specifically about using these as isotropic emitters, and then a full optimization after we've established some of the better properties of these emitters, and then we'll go into the conclusion and outlook. So we'll start with the interaction Hamiltonian, which consists of many terms, but today only the first two terms are important, the electric dipole transition and the magnetic dipole transition. And it's quite well known that in optical frequencies, the electric dipole transition dominates the magnetic dipole transition. Even for europium 3+, which has quite a strong magnetic dipole transition, second order effects such as Lycan field effects will still mean that this dominates. For example, you can see here the spontaneous emission from europium 3+. The electric dipole transition in red dominates that of the magnetic dipole transitions down here. And what we want to do is decrease this transmission and increase these transmissions. Because if we can do that, we can get a lot more control over the phase and amplitude of the reflected and transmitted waves, and as Alex was talking about, create a perfect absorber, for instance. So yes, we wish to design a resonator to suppress E and enhance the magnetic field. And this is essentially called the Purcell factor, which is the normalized enhancement of the decay rates, where gamma is a decay rate. So if we have a Purcell factor of 5, then the decay rate increases by about 5 times that the vacuum amount, and we can get a much brighter emitter. Because this magnetic emission does not couple to free space well, but we can make it couple to a different resonator. So to do that, we need to make a resonator which has an artificial dipole moment. Dipole moments, there's two, as I said, the electric dipole, which is just the oscillation of these two charges, and the magnetic dipole, which is a current loop with the magnetic field flowing through the loop. And so we want to imitate this in a material and increase the local density of states, magnetic states, that is. And this gives us two different Purcell factors, the magnetic Purcell factor and the electric Purcell factor. So there's been a good amount of research into this, and currently high index dielectric resonators are quite in topic because they have a low ohmic loss. They generally have high magnetic Purcell factors, but the problem is there's a very difficult fabrication route if there is one at all. Example of this resonator is a silicon core, silica core silicon shell resonator, and these can provide quite a large magnetic Purcell factor, but they there's no real manufacturing route. We also have plasmonic resonators, which generally have a larger ohmic loss, but we have a very clear fabrication route to making these resonators. Then separate to this, we have what I've called isotropic resonators, which is similar to this over here in that the Purcell factor is the same for a dipole that is oriented in any direction, and generally they have a lower peak Purcell factor compared to what I've called anisotropic resonators, which look, for example, like this hollow cylinder, where the magnetic dipole needs to be oriented in a specific direction. But along that direction, it has quite a high Purcell factor, but in other directions, it does not, which makes these a bit inefficient. And from there, Alex has already introduced these particles, but these are the particles I've been working with. We call them nanopods. This is an example of a dodecapod, which has 12 satellites, but I've looked at particles from 4 satellites through to 30 satellites. They consist of a silica core and a silver satellite and silver satellites. Again, as Alex said, these can be fabricated. The fabrication process is very, very broadly. I'm not an expert at all in this. I need to emphasize that. They start by nucleation of silica, or polystyrene clusters onto a silica core. The polystyrene clusters on the core, they can actually move a little bit. They have a slight positive charge and they can repel each other, or if the force is strong enough, they can join together. After that, we grow the styrene and then regrow the silica core around the styrene, remove the styrene, and eventually grow either gold, or we can also grow silver. And as you can see, these things exist. At ICMCB, they can make really nice particles. So the first thing that we had to do with the simulations was to actually figure out how the satellites arranged during synthesis and where to put the satellites in our simulation. And because these polystyrene nodules can move and repel each other a little bit, we decided to use solutions of the Thomson problem, which is basically, it's a problem where you have charges constrained on a sphere and you look at the energy minimization of the charges on that sphere. It's a fairly open problem and only a few solutions have been proved, but it's also quite a classic problem for optimization, for looking at optimization algorithms. The first two solutions for n equals 2 and n equals 3 we don't really care about, but starting from n equals 4 and going up, we get equivalent polyhedra which all have symmetries. And these symmetries, it turns out, will become very, very important. So I will show you, I should show you, yeah, I'll show you the symmetries of these particles. These are all of the ones that I've looked at, going from n equals 4 to n equals 30. And you can see that the symmetry order that they have, which is intrinsic to their equivalent polyhedra, is very different. As it turns out, I'd like to point out in particular these three solids, because these are platonic solids for n equals 4, 6, and 12. And you can see these all have the highest symmetry, but it turns out that tetrahedral symmetry is all that's required to have a good isotropic emitter. As a semantics note, when going forward, when I talk about, for example, a dodecapod, which is n equals 12, I'm talking about an equivalent polyhedra where the satellites are located at the face centers of a dodecahedron, not at the vertices of an icosahedron, which is the dodecahedron's dual. So the parameter space is extremely large. For example, we have the wavelength, the radius of the satellites and the core, the orientation of the dipole, and some location of the dipole. And we want an emitter where no matter where we place this dipole in the core here, that we will have, or what orientation the dipole is, we will have the same Purcell factor. And because of that, we have a huge parameter space. And if we were to do this with normal real frequency simulations, then it would take a very, very long time. So to deal with that, we have used quasi-normal modes, which are great because they only depend on the satellite and the core. I've used the freeware modal analysis of electromagnetic resonators, which was made by Philip Allan's group, and it's been really, really nice. And as I said, yeah, the modes only change with the satellite and the core radii. And once those are calculated, everything else can be calculated very quickly. So to give a brief overview, in general, we try to reconstruct the scattered field by solving a differential equation and determining the eigenvectors and eigenfrequencies. So the modal fields, from the modal fields, we can calculate the scattered field after we've determined this excitation coefficient, which we do as with an overlap integral, or in the case of dipoles, we project the dipole onto the modal field. Importantly, you can see we only care about the modal field at the location of the dipole. So this is extremely fast to do for either an electric or magnetic dipole. And from there, again, to calculate the Purcell factor, it's very fast. It's just a projection of the dipole onto the modal field again. And we can calculate the Purcell factor. Because we are using metallic particles and there is loss, like ohmic losses, we do also need to calculate the non-radiated Purcell factor, which we can do by integrating the intensity over the lossy regions. This integral takes a little bit longer because we have to integrate it over the whole these modal fields over the whole resonator. But regardless, this is still much faster than using real frequency simulations, because we get these 5 parameters down to just 2 parameters, and it scales much better with a bit of post-processing. So on to some results. The first thing we did, we wanted to figure out which resonators were good as isotropic resonators. So we fixed the radius of the core, and we excite the structures with the dipole at the center of the core. The radius of this core is 85 nanometers, and we excite them with an X, Y, and Z oriented dipole along with an average over many orientations. And to characterize them, we decided to find what we called rho, which is this vertical purple line here, and that is basically a variation in the Purcell factor of the particle due to randomly oriented dipoles. We have psi, which is this horizontal line here, which is basically a measure of how resistant the particle is to polydispersity in the satellite size. We also define the branching ratio, which ranges between 0 and 1, 1 being a perfect magnetic emitter, 0 being a perfect electric emitter, and then the quantum efficiency being 0 for a very bad emitter and 1 for a perfect emitter. Finally, that allows us to define a single figure of merit to characterize all of the particles, which takes into account the purity, the efficiency, a normalized factor which takes into account the randomness of the dipole orientation, and a normalized factor which takes into account the polydispersity considerations. And to show you just how much the symmetries here matter, if we take a particle which does have tetrahedral symmetry, all of these points overlay each other, and we get essentially a perfect a perfectly isotropic emitter, compared to this one where we have, which is actually a highly symmetric particle, but it has the wrong symmetries, where similar to the cylinder, where if we have the dipole oriented along this axis here, it gives us a very strong Purcell factor, but if it's at any other orientation, it gives a much lower Purcell factor. So to summarize this, on the left-hand side and in the blue, we have the magnetic Purcell factor, and on the right-hand side, and in the red, we have the symmetry order. These error bars, they are rho, so this vertical purple bar. And you can see that for the particles, in general, for the particles with high symmetry, we have almost no, we'll have almost perfect isotropic emitters, but for particles with very low symmetry, we have a lot of dispersity in the emission. The outliers are the particles for n equals 7 and n equals 14, where they have that highly symmetric system, but it's around a single axis, which is not very useful for what we want. We also looked at the satellite size of the optimized particles, and also the normalized factor here. And we found that the more particles you have, the more sensitive everything becomes to polydispersity, which is, I guess, quite unsurprising. Now, looking at the figure of merit, you can clearly see that the dodecapod is by far the best, but as I said before, all of the platonic solids, n equals 4, 6, and 12, are very good, as well as n equals 16, which has tetrahedral symmetry, is also very good. But in every case, or in almost every case, aside from n equals 4, we're able to get very good branching ratios and generally very good quantum efficiencies. The final thing we did here was to look at the volume and orientation averaged per cell factor. So instead, in this graph, instead of just exciting the dipole in the center of the core, I excited it at 100 different locations in the core. And we look at the variation in the per cell factor. And surprisingly, regardless of which particles we use, they're very, very resistant to where the emitter is located. But and that's what the error bars here are. That's the standard deviation of all of the excitations. Going on, looking at the actual spectral properties, this is for the dodecapod. We've optimized this with regard to the black dash line here, which is the magnetic emission of europium 3+. And as you can see, we can get a very strong magnetic per cell factor, which is this solid blue line, and a very small electric per cell factor, which is this dashed blue line. And again, we get very nice, very nice branching ratios in the solid red line and quantum efficiencies in the dashed red line. This is actually the orientation and volume averaged dipole. So for each wavelength here, there is almost 1,000, almost what would be 1,000 simulations if we were doing this via real frequencies. So the only reason that we can really do this is because we're using QNMs, and they make things much easier once they're calculated. And because of that, we can actually do this for all of the particles. And as you can see, in every case, we can optimize these systems for to get good properties at the wavelengths that we want. After this, we decided to change the radius of the core, and it's optimized for both. So for this, we used the downhill simplex algorithm with some basin hopping, and optimized it. And we can actually achieve some extremely large per cell factors, greater than 500, quite easily. The problem is that the polydispersity considerations become quite ridiculous for these, where the full width half maximum is very, very, very narrow. And this is just not achievable experimentally. But you can find more reasonable optimizations, which is good. For example, we found this one. This graph is shown at the optical properties at these points. So we have we still have a reasonably small psi, but we looked at this whole area around 4 nanometers, and we still get very good optical properties when we average over all of these particles, far in excess of the ones with larger cores where we have much larger values of psi, which is good. And you can see here, we still get radiated magnetic per cell factors of nearly 200, which is really good. And we still suppress the electric per cell factor very strongly, which again is really good. The branching ratio is very high. The quantum efficiency is not as good, but this generally happens with a larger satellite to core ratio. So for the conclusion, multipod clusters are very promising as isotropic magnetic emitters. We also were successfully able to use QNMs to drastically reduce the parameter space of the optimization. In terms of where to go, one problem with the QNMs in the way that we were using them was for the full optimization where we looked at both the core size and the satellite size. The dominant modes moved a lot, and unless I was able to have a good guess about where that dominant mode was, I wasn't always able to get good results with QNMs. There are other ways to find the QNMs, which I think could be helpful, for example, based on multiple scattering. Then I would also like to be able to include polydispersity in the optimization. With our collaborators, we're also fabricating the dodecapods with European 3+ emitters in the core, and that's going reasonably well. And finally, we'll be doing single particle characterization of these emitters in Paris with our collaborators there. So thank you all for listening, and in particular, thank you to these guys who have helped me a lot.